Up to now, we've done a lot of work around the normal distribution. We've looked a lot at the distribution of the mean. We see that it takes the same mean as the population may take, and we've looked at the sample standard deviation, the standard error, and the variance. We've seen how these change as the n value changes. Typically, we've spoken about that n value being large. We've been able to make use of this to find the confidence interval for the unknown population parameter mu. We've seen how this works really well when we know that n is large, because we can approximate, or we can calculate the sample standard deviation, and we can use that as an approximation for the population standard deviation. We can approximate the sample variance and use that as an approximation for the population variance. Up to now, this has been possible because we're relying on the sample to be large. We're doing this with large samples. We're not always guaranteed to have a lot of data or a large sample, so we need to consider what happens if we actually have a small sample size. Well, when the sample size is small, we can no longer standardize to a normal distribution. We can no longer rely on the normal distribution. And in fact, there is a different distribution that caters for this. This is the t-distribution. When we have a small sample size, an unknown population variance, we can actually do the same steps but apply them, model them with a t-distribution. That t-distribution is going to have n-1 degrees of freedom. So the sample size minus 1 is going to be the degrees of freedom. And we have a set of tables that we can use to look this up. Now the t-distribution does actually look quite a lot like the normal distribution. It has some of the same properties, it's symmetrical, it peaks in the middle, but it's a little bit more mound shaped. It's a little bit more peakish. It increases at a faster rate. So for low values of n, for small values of n, there is a difference between the probabilities and critical values we would calculate with the normal distribution, which is here in red, and the t-distribution, which is here in blue. But just to make this point for you, as the sample size increases, the t-distribution does start to take on the same shape as the normal distribution, which is why we're talking about small values of n lead us to use the t-distribution. Once n is significantly large enough, we're fine to go ahead and use the normal distribution. So in summary, if we do not know the population variance, two things may well happen. If we have a large sample size, because we can approximate S to sigma, we can model with the normal distribution. If we have a small sample size, we cannot approximate S to sigma, we can't model with the normal distribution, instead we revert to the t-distribution. So here are the tables that we'll use. They'll be found in all the normal places in your formula book, either that you've stored on your phone or that you can find online, or the ones that we have in the classroom. We're going to read the degrees of freedom from the column on the left hand side and the probability that we're considering from the row at the top. We'll just cross-reference these to find our critical values. We've used tables so often at this point that actually I'm sure you're quite competent at using these. These will be the last tables that we need to be familiar with for this course. Okay, so let's start by making sure that we're comfortable with using the tables for the t-distribution. So here we've been told that our random variable has a t-distribution with 10 degrees of freedom. So the v is going to be 10. We're asked to determine the value of t for which these following statements are going to be correct. So first, the probability that x is greater than t equals 0.025. Well, on your diagram, we're going to be looking at this right-hand tail, and this is the probability 0.025. Well, the probability the tables refer to is the probability exceeding your t value. So we'll just look up the column for 0.025. We're looking across for 10 degrees of freedom, and we get t equals 2.228. Okay, let's see what would happen if we had the inequality sign change. So the probability that x is less than t equals 0.95. Well, let's look at this on the diagram again. 95% being below my t-value means the t-value must be here on the right hand side. The tables don't have 95%. It's only going to have the amount that's exceeded by my t-value. If there's 95% below, that means there's 5% above. I can look up in the tables for that 5%. So this red region, 5%, that will be in the tables. So the t-value that has 5% above it, when we have 10 degrees of freedom, is t equals 1.812. Okay, what if I had the probability that x is less than t, but this time it was a small probability? So the probability that x is less than t equals 0.1. So that's 10%. Where would that be on my diagram? Well, it's going to be over here on the left-hand side. And this is my 10%. Well, the tables, once again, aren't set up to tell me less than probabilities. All the probabilities need to be greater than. So let's see if we can find an equivalent statement, an equivalent region that might be useful. So the t-distribution is symmetrical just like the normal distribution is, and we'll try and use some of those techniques. So if I was to reflect, this region is the same size as this shaded region. 0 is in the middle, so t in the black region corresponds with negative t in the red region. I can look up a value for this negative t, which I can then translate into positive t. So in the tables, we see that the t-score that has 10% above it is 1.372, which means the t-value, the original t-value from my diagram, must be negative 1.372. Okay, and just one more using the tables this way. So, the probability that the modulus of x is greater than t. Just to remind you, this modulus combines both a positive and a negative case of x, whereas the magnitude of the x value should be greater than t. This is easier to show on a diagram. So the x values, so anywhere along the x-axis, should be greater than t. If it's negative, it should be smaller than negative t. As in, if you were to force the x value to be positive, it will be greater than positive t. Okay, so we can actually write this out as those two separate statements. So the probability that x is greater than t plus the probability x is less than negative t. That should equal 0.05. Because of symmetry, that means for each of them, it should equal 0.025, 2.5%. So let's go with that. Probability that x is greater than 2 equals 0.025. And this actually is the same as what we did in the first example. So t, in this case, must equal 2.228. Okay, so just quickly, let's see how the tables can be used the other way around as well. So, can we find the probability for each of these statements? So if y has a distribution, or a t-distribution, with 4 degrees of freedom, I'll just write this like this, can we use that to determine the probability where y is greater than 3.747? Looking at the tables, we just need to go for the row for 4 degrees of freedom, and we're looking for the number 3.747, and when we find it, we'll just read up to see the probability that this belongs to, and here the probability is 1%, 0.01. Okay, similarly, the probability that y is less than negative 2.132, here's where it would be on a diagram. Our tables don't show us any values from the left-hand side, so we're going to need to use symmetry. So the probability that y is greater than 2.132 will be exactly the same as the probability that it's less than negative 2.132. So let's just look this up. When we find the 2.132, we read up to the top and we see 0.05 is the probability associated with that t-value. So if we were to start with the t-distribution, as I've shown you, and we wanted to calculate a confidence interval, the 95% confidence interval is going to have 2.5% in each of the tails. The critical values that correspond to the 2.5% at the top end and the 2.5% at the bottom end can be found by using the tables and finding those critical values. How could we then turn that into an expression for the limits on a confidence interval for the mean? Well, you've seen this before. We can start to rearrange. We're going to multiply the left, the middle, and the right hand side by s over root n. We're trying to isolate mu, so we can subtract x bar from the left, the middle, and the right. We're almost there. We have negative mu in the middle. We want it to be mu, so we're just going to negate each side. And just looking carefully, yes, the left-hand expression is the smallest, the right-hand expression is the largest. So x bar plus or minus our critical t value, s over root n. So hopefully this is familiar to how we found confidence intervals previously. Here's how we'll do it when we have an unknown population variance and we have a small sample size. Okay, now that we can comfortably use the tables to pull out a t-score, let's see if we can calculate a confidence interval. So in this question, we're told that a sample of 6 trout, so those are fish, are taken from a fish farm and they were caught. Their lengths were recorded in centimeters. Here's the data that was collected, assuming that they're normally distributed, so that's one of the assumptions we need to make use of. Find a 90% confidence interval for the mean length of the trout in the fish farm. Okay, let's just collect the data that we have. So firstly, n equals 6. We're looking for a 90% confidence interval, so we're going to do alpha over 2, so that's 10% divided by 2, 0.1 divided by 2, 0.05. Okay, what else do we need for the confidence interval? We're going to need to know the mean, so the x bar, and we're going to need to know the sample variance, or the sample standard deviation. I'm just going to type these numbers into the calculator. So these 6 values are going into list 1, frequencies of 1 into list 2, and on my summary screen I can get both x bar and the sample variance. So the degrees of freedom in this case is going to be 6 minus 1, it's n minus 1 to get 5. The 90% confidence interval is going to be a combination of the mean, so a way to talk about the middle, a critical value, which helps us to get the right spread, and the standard error, the standard deviation for the mean distribution. So x bar plus or minus the t critical value multiplied by s over root n. That's what we should be looking to use. So just substituting those values in, we get 25.5 plus or minus 2.015 multiplied by 0.9252 over root 6. Okay, just off to the calculator and we get those two boundary values, those two confidence interval limits, 24.739 and 26.261. That's the 90% confidence interval. In this question, we're told that the percentage starch content of potatoes is normally distributed. We need to know it's normally distributed with an unknown mean. In order to assess the mean value of the starch content, a random sample of 12 potatoes is selected and their starch content is measured. The percentages are shown and collected in this data. We're going to do the same thing for a 95% confidence interval for the mean. So let's go ahead and collect the data that we need. N is going to equal 12. Significance level is alpha over 2. 95% confidence interval means we do 5% divided by 2. Once again, x bar we're going to get from the summary screen of our calculator, and the sample standard deviation also comes from that summary screen. So x bar 20.675 and s is 1.5130. The degrees of freedom are going to be 11. 95% confidence interval, and this formula should be getting familiar now. An anchor point, a middle point, which is x bar. The critical value from the distribution, which is t with 11 degrees of freedom, 2.5%. And then a measure of spread, which is the standard error, or the x bar standard deviation. Substitute all of those values into our calculators. We get 19.714 and 21.636. So confidence intervals and using those tables, if we can practice those, that will really help us when it comes to problem solving questions and hypothesis testing later on.